Okay, so can you see my first slide okay?
You're up and running.
Up and running, perfect. Okay, thanks, Wes. As Wes said, so this is basically best practices which have been developed from actual deployments and experiences that we've done. So the three companies here are ARISTA, Imagine, and Telestream. We have a lot of experience doing PTP deployments. We've all been involved in defining the standards at the interops, the dirty hands events, the JTM tested events. So we have a lot of experience on very large designs as well as very small designs. We're basically here trying to help you be successful, and we want you to sort of learn from the sort of the mistakes and the successes that we've seen in the field. There is a lot of information here to cover in 30 minutes. If you want some additional background or additional information, Imagine, ARISTA, and Telestream, we did a three-part, 3-hour webinar series a few weeks ago, and we'll have some more information on that at the end. So if you want some more details, that's available. Just sort of some housekeeping here. During the course of this presentation, we'll be using terms such as master and slave, since this is the language that's used in the standards today. Please note that when we use these terms, we're referring to electronic devices and not to a person. Work is being carried out in standards organizations to change some of this terminology, and the standards will be updated in the future. So today we're basically going to look at best practices, and we sort of group them into 4 sort of major areas. One of them is looking at sort of the network, general sort of network architectures topologies. Some of them around very specific PTP network architectures. Then there's the PTP configurations that you'll do on your devices, and then looking at sort of commissioning and operating your system. And we're also going to try to cover both the what is the best practice and the why. There are a few cases, depending on your application, where you may want to sort of deviate a little bit from the best practices, and we want to make sure that you understand why we're recommending this as a best practice and what you have to be aware and sort of cautious of if you do deviate from those. Okay, with that, we're going to start with the sort of general networking architecture best practices, and I'm going to hand it over to Gerard now.
Hi, Leigh. Thank you very much. So, I'm just going to crack straight on with the best practices. So, best practice number 1 is to create a solid network and good PTP foundations. So, we're talking about PTP today, but some of the PTP best practice we'll share they're also fairly generic media network best practices. IP provides many benefits: scalability, future-proofing, flexibility. But in order to gain these benefits, there is some kind of upfront effort needed to identify the specific shape of your network. Many factors play into these considerations: the number of endpoints, building layout, whether it's campus or a central apparatus room type environment, for example, workflows, and of course, employee skill sets. These are all unique to your business, and as such, your network design will also be unique to your business. So you can see here a slide with 3 different sorts of architectures. We're not going to dive into those, and that's because the really good news is that these best practices can be applied to a wide range of different network scales and shapes, ranging from OB trucks through to multi-site, international scale, remote production type facilities. Next slide, please, Leigh. Just continuing a little bit on this kind of solid network and PTP foundation. 2110, you heard in the previous presentation, PTP has taken the place of tri-level syncs, black and burst signaling for facility synchronization. And as such, it's a really important part of the 2110 move. You need accurate and reliable PTP distribution. It's entirely vital. So the good news is that we can build this accuracy and reliability into the underlying IP network. You could bake it in if that's the way you want to see it. So some of the rules, some of the best practices we'll talk about today are covering exactly how to bake it in. In order to bake in accuracy, you need to make your infrastructure PTP aware. If you're making your infrastructure PTP aware, it follows you need to build on switches that support PTP at the scale that you're building your network at. That could be, 48 hosts per leaf switch, but it may well be hundreds of endpoints in a chassis-based system. So consider the scale that you're looking to build at, consider the switch's capabilities. You also need to avoid non-PTP aware switches. These will both reduce accuracy and scale. and typically they make configuration, troubleshooting, and monitoring of a PTP system way, way, way more complex. So might seem like you're saving some money, you're actually probably building yourself a stack of pain. And don't forget physical redundancy. On the drawing on the right, you'll see purple things. Those purple things are places where you can build physical redundancy into your network, and that will enable you to provide a network which is capable of supporting or continue to operate in more than one failure scenario. For example, multiple GMs, multiple PTP distribution switches, and multiple physical links between these elements. The level of fault tolerance that you choose to build in is entirely up to you and entirely tailorable to your needs. But basic recommendations would be not to kind of skimp on the places where you can make these things more tolerant. Cover this a little bit later in the presentation. Next, please, Leigh. So best practice number 2, choose a rooted network. I talked about physical resilience. Now let's cover a little bit about architectural resilience. We're building high bandwidth networks carrying enormous amounts of multicast. Andy talked about how we really are pushing switching infrastructure to the limits. He's absolutely right. We're pulling all sorts of COTS-based requirements out of, or we require lots of COTS-based features in our switches, but actually there's very few industries that need all of those COTS-based features at the same time. PTP, multicast, scale, throughput. It's we're really asking some big asks here. To make your life easier, I'd thoroughly recommend layer 3 infrastructure. Rooted networks have so many advantages. You're limiting the scale of your layer 2 failure domains. You're reducing the blast radius in the case of any sort of an issue with an endpoint that is causing trouble. Those problems, typical problems, would be flooding of a badly configured sender, or senders that are physically connected maybe to the wrong port, to the wrong switch, causing problems. So it follows therefore that if best practice is to limit the layer 2 domain size, then scale, which we talked about already, can only really be achieved by routing. So by building a network that protects against large failure domains by routing between many smaller failure domains. That is the essence of this best practice number 2. Routing also brings the advantage of better resource usage, providing active leaf-spine connectivity, avoiding spanning trees, loop prevention methods, which basically is just to shut links down and limit the bandwidth you've got available from the physical devices that you've connected together. And of course, again, avoiding the complexity of spanning tree configuration. Next slide. So if we're looking to go with rooted networks where we can, but if you're forced to work with layer 2, let's have a little bit of think about that. There's often cases where layer 2 seems attractive. There's legacy type environments, and sometimes the audio guys, they've been using layer 2 for a long time. So I just want to point out why it is the best practice really to go with layer 3. Here's layer 2. We've got 2 switches connected together, a single layer 2 domain. What we have is in a layer 2 domain, we have the problem that, or the behavior of multicast, that multicast will flood towards the querier in that layer 2 domain. What we end up with is that flooding towards the querier is unavoidable. It's part of multicast, fundamental to multicast. And so you can design systems this way, but the penalty is that much more thought has to be put into considering those workflows and how the flooding might impact on the system performance. You're going to spend a lot more time and effort having to mitigate these potential problems. Next slide, I think, Leigh. So let's talk a little bit about some more best practices. Number 4, use boundary clocks everywhere that you can. It's pretty simple, but it's a very powerful best practice. PTP-aware network infrastructure can operate in either transparent clock mode or boundary clock mode. Both provide good accuracy, but boundary clocks have a number of other benefits that are really valuable. Boundary clocks simplify the architecture and design by removing the need for multicast transport. All the links in the diagram, for example, are point-to-point links, boundary clock to boundary clock to GM, boundary clock to ordinary clock. You can get this type of architecture up and running independently of your multicast configuration very, very quickly. And you can simplify the debug of any issues by being able to focus on specific point-to-point problems rather than trying to debug network-wide multicast to begin with. Installation, debug, maintenance also massively simplified, as there's tons of PTP metadata that's available in the boundary clock instances in the network. You can identify the GMs, the parent clocks, BMCA events, and tons of message counter information, quickly focusing on the problems that may exist. They also, really importantly, reduce the load on endpoints on the GM and on the media nodes. That's a real factor in enabling scaling. Each endpoint only sees one set of messages. They see their own upstream master or leader messages. Next, please, Leigh. So just want to touch on a subject I always get a lot of conversations about, PTP version 2 and PTP version 1. Avoid PTP version 1 if you absolutely, unless you absolutely can't. Audio has been IP for ages, and one of the legacy issues is that there's a lot of PTP version 1 in it. Version 1 is not forwards or backwards compatible with version 2, and it's basically an obsolete standard. So support in PTP enabled switches is pretty limited. The easiest way to avoid it is to have a chat with your vendors, your audio vendors, because most audio kit can run version 2. Most audio standards don't mandate version 1, they enable either. So what happens if you can't avoid it? Well, if you can't avoid it, then the next best alternative is to run isolated PTP subsystem for version 1. Typically, this would be non-aware because that's historically how it's been, because the scale and the accuracy haven't needed it. But if you need to synchronize your separated version 1 network to your version 2 network, then most audio vendors will have the opportunity to, will be able to offer you a PTP version 2 to PTP version 1 boundary clock that will essentially bridge across and synchronize them together. So I think at this point, on to the next slide, but I will also hand across to Mike from Telestream.
So a difference in time between the Grandmaster A and B will likely cause a shock to the system, and media node devices would potentially see a disturbance in their output. You want to make sure that this does not happen in your system, and therefore it's recommended to use GPS reference for both SPGs that will generate the master clock. Then when switching between the two Grandmasters, there should be no disruption or sync shock to the system, and this would obviously need to be tested during the commissioning phase. There should be an external link between the two boundary clock switches specifically for PTP, so that the GM will be used across the network based on the best master clock algorithm. Since both devices are locked to GPS and have priority 1 and 2 as shown, then the Grandmaster A would be chosen and Grandmaster B would be in passive mode in this case. Now let's take a look at the next slide. So in this particular case, we're going to widen that to a larger network. Remember, if you have questions on Precision Time Protocol, PTP, please join us in Presentation Area 2 after the presentation, where you can ask your questions to the panel. Now for this distributed network, it's recommended that each site have their own active Grandmaster that is locked to GPS. This means each site will be locked to a known time reference, and each site will have a common master clock. One may consider to use that network itself to carry PTP across each site. However, PTP is reliant on synchronization of both forward and reverse path. A wider area network potentially may have a greater variance in the forward and reverse paths that could potentially cause problems for maintaining synchronization. You will notice, however, that each site could have a primary and secondary network for redundancy. And Leigh is going to discuss this topic next.
Yeah, so when you're looking at, in a lot of Essence networks, you're going to use 2022-7 for your redundancy. And the one thing to note is that the redundancy model of 2022-7 and PTP and its BMCA are very different. So you have to be sort of careful how you're connecting these two very different methodologies. Note that sort of SMPTE is working on sort of standardization, some recommended practices around this, and do expect some sort of future webinars on this area. But at a very high level, what you want to make sure is that the network must converge to a single grandmaster in the event of a failure. So if a grandmaster fails, if a link fails, if a switch fails, you want to make sure that it all converges to a single grandmaster. So because of that, we don't want a 100% air gap network. So often on the -7, you sort of think about having completely air gapped. And because of PTP, you do not want that. So you need to have at least sort of 2 links between the 2 sides. This might be done very high level close to the grandmasters, or this could be a little bit lower in your network, depending on how you decide your network. But ultimately, you need to have connectivity between the 2 sides, at least just for the PTP packets, so that you can sort of make sure that everything converges to a single grandmaster. So now moving into looking at PTP configurations. So in terms of choosing your values for your message rates, you basically want to use the values which are in the 2059-2 2020 default values. This isn't published, but it will be published very shortly. AS67 and SMPTE profiles had some slightly different defaults. We created this document called ASR16, which sort of tried to reconcile that. And the values that have been come up with have been basically been tested very thoroughly at all the various interops, dirty hands events, the JTM tested. They've been deployed very well in the field. A lot of people sort of thought different trade-offs between rates and complexity and so on. And so these numbers are sort of been very well tested and are basically, there's very few good reasons why you would ever want to deviate from them. And basically the values are an announce interval of 0 or 1 message per second, an announce timeout of 3, a sync interval of -3, which means 8 messages per second, and a delay request of -3 or 8 messages per second. So these are the values you should use in every deployment. There's something called the SMPTE 2059-2 TLV message. So this is something which was added in the SMPTE profile, and it basically allows media nodes to generate drop frame timecode. As we moved to PTP, we needed a way to basically emulate how drop frame timecode is done. And these are special messages sent from the grandmasters. Now, you may ask yourself, why should I turn on these messages if I'm not actually using drop frame timecode? The reason you basically want to do this is you want to avoid issues in the future. One thing we found as we've done various testings and field deployments is that there's been some implementations have had some bugs and some issues related to the TLV messages. And if you turn it on while you're doing the initial commissioning of your system, then you can work through these issues, you can get the code updates, and you can have a system that supports the TLV messages properly. If you decide to do it later, you may add one device to your network and you say, oh, that device needs the TLV messages, I'll turn it on. And at that point, you have a live system, you turn on these messages, you may uncover some issues which may cause more sort of on-air type events. So you want to sort of do it at the beginning of your project, when you're doing the commissioning, when you're doing your thorough testing. Much better just to sort of sort it out at the beginning, and then it'll make it very easy in the future. You can just flip it on and no issues. Another configuration you want to do is something called the PTP role master. And you want to basically do this on all the ports that are facing your media nodes. So in all our networks, these are engineered networks, so we know where our grandmasters are. And so we know which are legitimate interfaces where a master could exist. By turning on this feature, and you must be in BC mode to be able to have this feature, if you turn this feature on, it basically prevents any rogue masters or badly configured endpoints taking over the network, which is something you don't want to do. So this is a very important sort of security mechanism to sort of, it hardens your PTP network substantially by just turning on this simple feature. A sort of supplemental thing to even increase it a bit more is on the media nodes, you want to do sort of a slave or follow only mode so that those nodes will never ever try to become the master of your network because they weren't designed to do it. You don't want them to becoming it. But doing that role master is sort of a second level and a much more important level because it will prevent against someone who's even like actively trying to attack your network. And then over to Mike.
So the domain value provides a logical grouping of devices that are synchronized together using PTP. And you can choose a value between 0 and 127. For instance, SMPTE 2059 has defined a domain value of 127, while AES67 and IEEE 1588 have a defined value of 0. Therefore, audio devices are likely to choose a value of 0 for their default, and media nodes are likely to choose a value of 127. This means that when you add a new device to your network, and you're using 127 or 0 for your domain, then that device will automatically be associated with all your other devices on the domain. Your new device may not be fully configured for your network and could potentially become the grandmaster or cause a disturbance to the PTP network. Therefore, it's recommended not to use the default values, so that a new device has to be specifically configured for your PTP network to avoid potential problems. Let's move to best practice number 13. And in this case, choosing your priority 1 and priority 2 values appropriately in your network, creating a suitable hierarchy of logical processing for choosing which device is going to be the grandmaster. In this case here, we want the SPGs to be chosen the grandmaster over the boundary clock. So the SPGs have a smaller value for priority 1 than the boundary clock. This means the value of the clock class, the clock accuracy, the clock variance, and priority 2 will determine the grandmaster. And if both devices were locked to GPS, then grandmaster A would be chosen. If there was a connection failure for the SPGs, then the priority 1 of 10 for the boundary clocks would be next to be chosen. You could have even more multiple levels for determination of the grandmaster depending on your network configuration. But by having these multiple P1 levels, it helps in the convergence of the PTP network to the grandmaster. Now, Leigh is going to discuss some of the best practices for commissioning and operation.
Okay, so if you follow these best practices, now you've designed and built your system. Now you need to verify that it's working correctly. The one thing to watch out for is that PTP can appear to be working when it's really not. It may not be locking as fast as you want, or in the case of a failover, it may not fail over properly. So there's subtle things where it seems to work, but it's not really. And these issues can be because of your design mistakes in your original design. Some devices may be missing features you expect. There may be configuration errors, or there could even be implementation bugs. We've seen all of the above. Just a few things. When you're looking at a PTP system, there's basically 3 main elements. And you also notice that these are sort of matched to the 3 companies that are doing this presentation. And you have media nodes. And these are the 3 key elements of your PTP system. So best practice number 14, a commissioning checklist here. So as you're doing your commissioning, you'll have separate checklists for the grandmasters of switches and the media nodes, because each of them have their own sort of parameters and key things that you want to check out. Things like a switch will basically, the checklist will be a combination of both a grandmaster and a media node, because it effectively behaves as both. These checklists are quite long. There's a lot of things you want to check. And for each element, you'll basically work out a pass-fail criteria. So you'll have an item that you want to test. You'll have what's the expected value. Say the message rate is -3, so I expect 8 messages per second. You'll do some tests to verify, is the message rate approximately 8 messages per second, and is it within the range that you want? And then you'll either pass and fail that item. As you go through all these checklists, once you're done, then your system has sort of been fully commissioned, and you know that it's going to work as expected. When you're doing your commissioning, you want to be doing, part of it will be doing sort of like PCAPs to make sure that all the packets and stuff are correct. When you're doing your commissioning, you want to run the system for at least 24 to 48 hours. We found that there's been some failures in some devices that occur very randomly, but within sort of 24 to 48 hour period, all the issues, if they're going to occur, will generally occur. Now, doing a PCAP, you may think doing a PCAP for 48 hours seems kind of massive, but the thing to remember is that these message rates are very low. And so doing a PCAP of 48 hours for PTP packets is only a couple hundred megs, and that file is actually quite manageable. You'll be using various tools. The devices have APIs and GUIs that you can extract various counters, things like Wireshark, and there's various test and measurement equipment that you'll need to use. One important part of the commission is you do want to test your redundancy and your failover and your power up. So you want to basically understand, if this particular link fails, if this device fails, what is the expected behavior? How does the BMCA take over? How will the media node see this? So you need to work out very detailed transient behaviors of what's happening, what the port changes, and the timing of all these events. And just note that some very subtle things, like if it's the antenna fails versus the device, it actually has, I mean, the end result is the same, but the transient states in the middle can be quite different. And a very important thing when you're doing all this testing here is a change of grandmaster should have no impact on the media node. So yes, the grandmaster ID changes. As Mike said, one of the earlier best practices is that because all the grandmasters have effectively the same time, as you switch from one grandmaster to the other, there should be no glitches, there should be no change in phasing, there should be no effect on your device. So it's very important as you're doing these testing that we want to make sure that nothing like this happens. Best practice number 15, our last best practice, is you want to have a monitoring solution. So you want to be looking at sort of critical parameters, things like the grandmaster ID, the locking status. You want to be able to sort of check to see if there's been a change in the state that's going to detect failures occurring or maybe someone's attacking your system. Just so everyone is aware that SMPTE does have a drafting group that's working on this. It's the PTP monitoring group, and they're working on something called RP 2059-15. This is going for a public committee review process, so do expect in the near future seeing this document available for everyone to look at. Key thing that it's doing is sort of standardize the parameters and the encoding. Issue you have is that one device might say locked, another device might have not locked, another device may not have locked at all. And so this document is defining standardized parameters and a way to do that. Note that in the new version of 1588, the version 2.1 that was recently published, it's added some new features around this. And that you do want to have some sort of monitoring device that can basically collect all this information and analyze it. Okay, so just to review here. So we have our best practice number 1, start with a very solid network and start foundation. You want to use, so best practice number 2, you want to use a routed network wherever possible. If you can't do a routed network with layer 2, note that there's some sort of things you want to be very cautious of with the layer 2 networks. From a PTP architectural point of view, you want to use boundary clocks wherever you can. You want to use PTP v2 and avoid v1 if you can. It's critical that all the grandmasters have the same time, so if you do have a failover, there's going to be no time discontinuities in your network. If you do have a multi-site, you want to make sure that you have an active GM at each site. If you are using 2022-7 for your essence redundancy, it's critical that you have the connections between those two sides so that the network will always converge to the same time. From the configuration point of view, you want to use the 2059-2 2020, the not yet published but soon to be published default values that I mentioned earlier. You want to turn on those TLV messages. You want to use that role master on all the ports which are facing media nodes, or conversely, basically put it on every port except for the ones which you can trace back to your grandmaster. You want to set the PTP domain not to the sort of the default of 0 or 127. You want to pick a different value. You want to set the devices at the same level, have the same P1 value, but different P2 values, so that you can basically control the BMC algorithm and who's going to be the master in a controlled manner. During the commissioning, you want to make sure that you go through a proper commissioning phase, have these detailed checklists, do a very thorough analysis, because your devices may seem to be working when they're not. You want to have a PTP monitoring solution, which can assist in your commissioning, but also gives you sort of permanent monitoring of your system to detect any anomalies or issues, degradations. Kind of remember that of all your essence flows and PTP flows, the PTP is the most important multicast in your network. And if you basically follow these best practices that our 3 companies have come up with, you will have a very successful PTP deployment. It will work very well. It'll be problem-free. If you do have sort of if you're interested in seeing those webinars I mentioned,